Okay, so let's just review real fast then. That was good timing. Let me first hit the light. Welcome back to first hour. It looks like Kylie's donation definitely will take us over 500. So we're halfway to our goal with 2 days left.
I swear.
She will swear.
I will swear.
Um, I was going to give a bag of food to Bert's party last night, but they never came to my house. So I will donate. It was about 25 pounds. So that I can drop my lowest grade in this class also. All right, so let's just quickly review. We said the principal quantum number. We're going to talk about 3 numbers and then another one. Oh, that sounds weird. That would be 4. But just stick with me. 3 that are important and then another one. All right, and we said that this principal quantum number that we're going to come up is equal to the row value, or row number. You all right with that? Okay, then we'll get to all this in a second. But the next thing I want to talk about is this slide, is what we call the azimuthal quantum number, or L. Now, I usually write a cursive L. So if you see me write a cursive L, that's what that is. This quantum number defines the shape of the orbital. Oh, yeah, we talked about this. I can see that I already drew the table for you. The allowed values of L are integers ranging from 0 to n-1. We use letter designations to communicate the different values of L and therefore the shapes and types of orbitals. So just real quick, if n equals 2, then L has 2 options that it could be, which are what? It could be 0 or 1. How come it cannot be 2? All right, because L is equal to n-1. You okay with that? All right, if n equals 1, the only options are what then? Okay, so let me say one more, let me say it in a different way. If my row of my thing I'm talking about is in the first row, my L value can only be what? A 0. Now, I gave you just a little table. What does a 0 correspond to in shapeland? S, right? Okay, so in the first row, the only allowed shape would be what then? A sphere. Sort of with me? Okay, but now let's say I'm in the second row. The second row means n equals 2, and L could be 0 or 1, right? Or in other words, if n equals 2, I could have a 0, which is what shape? A sphere. Or I could have, what's 1 equal to? P clouds. You with me? Go ahead, Caleb. No, because it went to 0. It was n-1 down to 0. The next number can be negative, but not. You sort of with me? If I'm in the third row, what are the allowed values of L? Which would mean in the third row, I could have S, P's, and D's. You okay with that? The D clouds are the 4-leaf clover ones. And there's 5 of them. And there's a reason why. How many P clouds are there? Okay, so first off, we'll say S, there's just spheres, right? A P, there was one of these, one of those, and one of those, right? And then a D, it looked like, whatever, that looks like a popcorn kernel, but whatever. And we said there was 5 of those, right? And then F, we said, F looked like that, and there was 7 of them. You with me? Okay. Now, there's a reason why we have 2, 3, 5, and 7. Did I tell you eventually those would come back? I said, remember these numbers somewhere? Oh, I said 2, 6, 10, 14. That's the same. Just trust me, it's the same. All right. And here's the reason why. Right here. The next quantum number is called the magnetic quantum number, or ML. This describes the three-dimensional orientation of the orbit. Like, is it up, down? Is it left, right? Is it in, out? Is it north, south, east, west, whatever? All right? The values that are acceptable for ML are negative L to 1. Or sorry, not to 1. Negative L to positive L. Therefore, on any given energy level, there can be up to 1s, 3p, 5d, 7f orbitals, etc. Now, I don't expect that to make sense, but I think it will here in a second. Is anyone writing stuff from the slide I need to wait for? Okay, you write. I'll get some liquid refreshment. So let's go ahead and do this. All right. So we have N, we have L, and we have ML. You with me? So let's see here. If I tell you that N is equal to 1, then L can only be equal to what? 0. And ML can only be equal to what? 0. Now, remember, the shape that corresponds, well, let's just write it over here. So this would be an S, right? Or a sphere. That's the shape, whatever, that's a sphere. That is equal to the L being 0. And if you think about a ball in space, do we care about its orientation? Like, nothing is different no matter what way it faces, right? Okay, so its magnetic quantum number doesn't matter. It has one orientation. All right, now, if I now have n equals 2, so n will be 2. What were the allowed values here then of L? 0 and 1, or S and P. All right? And then we know 0 is a sphere, so let's talk about what values you could have over here. 0 would just be the S, and then the 1, for my ML, I want you to think, it's between negative L and positive L. So it would be negative 1, 0, and positive 1 are your allowed values for that. Thank goodness for a mute button. All right. So if you think, how many values were there? How many different values are there for the 1? 3. These values correspond to the up and the down. the left and the right, and the in and out. So there are 3 orientations of the P clouds. Are you okay with that? All right. Those orientations are defined by these quantum numbers. It's called the magnetic quantum number. Who's with me?
So, to get the magnetic quantum number, it's negative L and then
What's that?
1. Is that supposed to be L or 1?
It's a L. I said 1 on accident. So it's negative L to positive L, including 0. All right. So let's go one more further, and then we'll kind of wrap this up. When n is equal to 3, what are the available options for L? No, not that's ML. 0, 1, and 2. So the 0 will still just have one orientation. The P would still just have these 3. Are you with me? But now this is a D cloud, right? So a D cloud, what would be the numerical values for this quantum number? Okay, negative 2, negative 1, 0, 1, and 2. Now, if you remember, I said a D cloud had how many? It had 5 popcorn kernels, Lucky Charms, whatever we're talking about, and they're defined right there. 1, 2, 3, 4, 5 different orientations. Are you with me? All right. An F, we'd have to be in the 4th row, and we'd end up with a 3, right? And that'd be my F. It would be negative 3, negative 2, negative 1, 0, 1, 2, 3. You okay with that? Or it would have 1, 2, 3, 4, 5, 6, 7 orientations in space. I don't know how to do that dance, but 7 ways that it orients itself in space around the nucleus. You with me? Okay. So yesterday I said, remember the numbers 2, 6, 10, and 14, right? Okay. Each one of these clouds can hold how many electrons? 2. So if S has 1 orientation, how many total electrons can fit in an S cloud? 2. If a P cloud has 3 different orientations, and each one can hold 2, a P cloud can hold how many? 6. And then I have my D. Each one can hold 2, so this would hold how many? 10 total, and this would hold how many? 14 total. Kind of with me? Now let's talk about how this random thing and the periodic table miraculously are exactly the same. Are you with me? You ever wonder why the periodic table isn't just a rectangle? Because really, if you look at it, that's so inefficient. Why would they construct it that way? Well, it's because that's how it works. All right, I'm going to draw the periodic table like this. And it's not to scale, but it's supposed to match the one over to my left. Do you see that? Okay. There are 4 distinct parts of the periodic table. There is this part. There's this part right here. There is this part right here. And there's this part. You with me? All right. Then I might as well, I guess, put the ones up here. So this would be H. I don't know where I'll fit this, but oh, it is. That's HE. You with me? Okay. Can someone tell me what row the top one is? Row number 1. Which means my first number for N is 1, right? Which means L has to be what number? 0, which corresponds to what shape? A sphere. And a sphere can hold a maximum of how many electrons? 2. So there's a reason why there's only 2 atoms associated with the top row of the periodic table. If n equals 1, the maximum you can have is 2 electrons. Helium has how many total electrons? 2. All right, we go down to the second row. With me? All right, the second row, and there's two columns here. I'll try, but whatever. Oh. Whenever I try to go slow, it gets worse. But whatever. There are two columns of atoms in that part, right? All right. If this is 2, well, the first thing we would fill is an S, or well, the first quantum number we would have is a 0, which would correspond to the spheres, and it would hold how many electrons? 2. But now, in the second row, we still have this chunk over here that we run into, right? And so if n was 2, the two values of L were equal to 0 and 1, right? All right, so now we're over here and we're at L equals 1, which corresponds to the P clouds. You with me? All right, there are 3 P clouds and they can hold how many each? 2 for a total of 6. Look at this part of the periodic table over there. Is it 6 atoms wide? Yes, it is. Now, these atoms that are over here, they are filling what shape of clouds? The up, down, left, right, in and out, right? But what letter? P. These elements over here we call P block elements. Any guesses what we call this skinny vertical column here? S block elements. Carrying on with that idea, what do you think we call this block? D block elements. And then F block. Say that again.
What is the shape of SFDP instead of SPDF?
It does go SPDF. And it might be a little tricky, but it's because we go down like a snake. Oh, hey, Tom. Hey, now. That was a disaster. Does that kind of make sense? We go S, then we go P, then we go S, then we go P, then we go S, we go P, then we go S, then we go D all of a sudden, because it's in the way. Then we go P, then we go S, then we go D, then we go P, then we go S, and all of a sudden F. Then D, then P. It's tricky, but you're going to learn it today. But can you sort of see how this random idea of quantum numbers and the structure of the periodic table sort of makes sense? All right? Now, quantum numbers are on your exam. So we better ask you some questions so that you can answer them. On the exam, I will ask, and there's not a lot on quantum numbers. The stuff we're about to learn is more important, but knowing what they are helps. The questions on the test will say which set of quantum numbers is not whatever is not allowed. Okay? And what it will do is give you A. It'll be like 3, 2, 1, 0. Don't worry about the last number for right now. Sorry. We'll just go with 3 since I haven't taught you the last one. B would be like 3, 3, 1. C would be 2, 1, 1. D would be like 3, 0, 0. One of those is not an acceptable set of quantum numbers. Which one is it? Okay, good. The answer here is B. And don't say, I don't get it. Say, oh, I need to get this. The first number we never care about, right? It can be whatever number it feels like as long as it's a whole number that's not negative. But the second one has a rule, and it's governed on what the first number is. The second one has to be at least 1 less than the first number. You with me? Is 3 1 less than 2? No, so it's not allowed. We don't have F clouds in the third row, I promise you. Sort of with me on that? Okay. You'll have that question on there. It's in the multiple choice. It's not the hardest question you'll ever have asked. And then I can't think of what the other ones are. There's more. I'll remember before Friday. All right. Now, there is a fourth quantum number. Huh. It's okay. I don't know where it's at, but it's called the MS, or the spin quantum number. And it's really not that important, but there is a fourth one, so you should know about it. The values of MS are plus 1/2 or minus 1/2, and those are your only two options. And you can pick whichever one you want. All right. What this is saying is all these numbers, the quantum numbers are describing the outermost electron in an atom. So it's describing an electron. You all right with that? Well, it turns out in this world that electrons spin. And they either spin counterclockwise or they spin clockwise. Because they chose that. Because they want it to add to 1 or 0. It doesn't really matter, but it's 1/2. Go ahead. Sure it would. And it doesn't really matter until you have two electrons together. And we're going to do this today. When we talk about these and we draw these electron configuration boxes, don't draw it yet, but we'll draw them like this. Because really, in an electron cloud, you have two electrons that hate each other, right? But we're forcing them to be together. The way that they are together is they both have opposite spins. That creates less resistance between them. So all that matters, you don't even have to know if it is a plus or a minus. All you have to know is if two are together, well, one of them is a plus and one is a negative. That's all you have to know. And that's why when I do these boxes here in 10 minutes, one's going to be a half arrow up and one's going to be a half arrow down. You all right with that? Okay, but really in your life, they are very not that important. Just know if you write 4 quantum numbers, pick either plus 1/2 or minus 1/2, whichever one's your favorite one to write, and always throw it at the end. You with me? Okay. I feel like that stuff's great. There's the spin quantum number. All right. So now what we're going to do, I don't really want you to write much of this. I just want to go with the flow. What I'm going to teach you now is what we call electron configuration. And it's our language to describe the electrons that we've been talking about this entire time. And if you've had chemistry before, you know this ultimately is super easy. It's a little bit harder for you because you're an AP student and we go past 4S. But if some of the lecture part doesn't make sense, know that ultimately this process in the end is really simple. All right. In an electron configuration, it's our language to describe how the electrons in an atom arrange themselves around the nucleus. Are you okay with that? So we all have Thanksgiving coming up. And if you always go to the same place and you're always with the same people, you may already know where you're going to sit. Does anyone already know where they're going to sit for Thanksgiving? Someone already know who they'll sit by for Thanksgiving? Just 2 of you. That's all right. I'm sorry. I like eating and watching football, but everything else about it I hate. Wow.
I mean, yeah, I mean, I'll stuff it to my face until I can't walk anymore, but like food's not my favorite, but I still eat it.
Yeah, I don't like turkey or yams or stuffing
Oh, it's so
or
good.
baked potatoes or mashed, I mean. But I like Thanksgiving. I like watching football. Okay. All right. So this electron configuration has a couple of ideas. First off, when we add an electron to an atom, it goes to what we call the lowest available. Oh boy, I can't spell big words, so just ignore me. Lowest available energy. Wow, energy level first. Yeah, it is a good thing I'm a chemistry teacher. All right, so just stick with me. I'll make this make sense in a minute. But first off, essentially, we're building something we start at the bottom. That's not that hard, right? How many of you in here did have chemistry last year? Again, raise your hands. Okay. All right. The next thing is we have to fill a row before we go up. Now, by the way, it's like I'm trying to tell you the rules to football, but you've never seen football, and I'm not going to show you to football until after. So it's a little tricky, but after you're like, oh, well, that makes sense. Although, have you ever tried to explain football to someone that doesn't get it? It is one of the most complicated sports ever created. I've been married for 15 years and still have not effectively communicated the rules to football to my wife. All right. On a row, electrons won't pair until they have to. Okay, we might add more to this list, so leave like an inch or two, and then we'll start applying this. All right. You need me to go back still? Sorry. All right, then what I want you to do in your notes, and really if you had chem already, you probably already know this, so you don't have to do these if you don't want. But I want you to draw this strange system of boxes. Better move those all down. Oh, thank you for nothing. And for right now, we're going to pretend that the world ends right there. That's all they had to do with normal chemistry. You'll have to do a little bit more eventually. Why do you do that to me? Like, it doesn't do it when I want it to, and it does do it when I don't want it to. Ooh, before I do that, hold on. You should label these. We're going to put a 1s right here, a 2s, a 2p, a 3s, a 3p, and a 4s. And then I'll group all this and lock it into place. All right. So this is a tool we will use to do what we're going to do for today. It's hopefully a tool that I'll teach you how to use, and then pretty quickly you won't need to use it anymore because you'll be able to remove it. It's kind of the scaffolding, and then it goes away as everything gets a little bit more solid in your head. So to find the electron configuration, which is how electrons arrange themselves around a nucleus in an atom, the first thing you need to do is talk about what atom you're talking about. So let's just randomly, we'll say we're going to use magnesium. Okay? So for this example, I'm choosing to talk about magnesium. So step number one is to figure out how many electrons does magnesium have. So you look over at that periodic table, the electrons is a smaller number, so how many electrons does it have? It has 12. You okay with that? Okay. Every single one of these boxes can hold, how many electrons would you guess? 2 electrons. So what I'm going to do is follow the 3 rules I just said. Number 1, I said start at the bottom. So I'm going to put all 12 electrons in these boxes. And I'm going to start at the bottom, which is 1, and I put 1 in. And then what do I do with the next one? I put it in this box, right? That was easy. I've accounted for 2 of the 12. What do I need to do next? I go up. So I put 1 here and then 1 down there. And now I'm at 4, right? And then what? Right. Yep. So the third row, or the third rule, I said, in the same row, don't pair until you have to, right? So the next 3 would go singly in a box. You all right with that? Now, I'm not there yet. I'm at 7, right? So the next 3, now you have to pair, because you can't go up until you're full. So now pair these. And I've accounted for how many now? 10. So I need 2 more. They go in the S box, and I'm good. Now, how come this last step I didn't go here and there? Okay. I can't go up until the boxes are full, right? I can go sideways one at a time, but I can't go up one at a time. All right. So here we go. Whoops. That was not super hard so far. You with me? Now, this is the tool. Remember, the answer, I'll just write it over here. The answer is the configuration. It's our new language, and you write everything that you just did. So you write the row, the shape, and how many you put in it. So it starts off 1s, and then a superscript 2. And that's representing what we did right here. You with me? Then the next thing I did, I went 2s. And how many did I put in it? 2. And that represents this. And then I went to 2p. And how many did I put in it? 6. And that represented that row. And then I got to 3s. And how many did I put in that? 2. Yes, ma'am.
So is it completely necessary to write everything except for the last one? Like, even the last one?
Eventually, probably tomorrow, we will write this as NE bracket 3s2. But that's for her. Everyone else ignore that question. All right. Now, can someone tell me what row is magnesium in? It's in the 3rd row, right? Can someone tell me what shape it fills? S. It's in the S block, right? Can someone tell me how far over it is in the S? It's the 2nd column over. That? Periodic table? Genius. Electron configuration? Mind-blowing. Right? This isn't that bad, is it? Even Kylie can accept this is not that bad, right? And she hates everything in this class. Yes? Sort of. Such a great question. And this is where chemistry sucks. After 4s, and I would love to go back in time and just punch someone. After 4s, it actually goes to 3d. And there's a reason. I know. I know. Don't worry about it. We'll get there. Even today we will. Yes?
So, if the orbitals are all filled up in S and P, then why is magnesium still not filled up on its outer shell?
Okay. Because everything wants to be like this. Because look, it is not filled up on its outer shell. The outer shell includes the 3p. So what would magnesium like to do? It would like to lose those 2, right? And then its outer shell is the 2, and now it's completely full. Really good question, but it makes reactions make sense, right? Okay. Who votes that this wasn't that bad? Even the TA. It's her third time all year. She's like, I could do this backwards, left-handed with no hands. All right. Let's do one on your own. And for now, we're going to stay between 0 and 20. So how about we do oxygen? Now, you don't have to fill in the boxes if you don't need them. If you do need them, awesome. Eventually you won't. What? Oh, it's a Wednesday, huh? Crap. It's a Wednesday. The bell's about to ring. In case you're wondering, though, the answer is 1, 2, 3, 4, 5, 6, 7, 8.
I was actually just going to ask that question too, but we just did this.
It's that answer. Be okay with that? Does it ring at 35?
I got 35.
40. Okay, how many had that? Okay, let's ask the same question. Can someone tell me what row oxygen is in? Second row. Can you tell me what shape of cloud its electrons are filling? All right, the S and the P, right? Can you tell me how far over it is in the P block? 4, or you could tell me it is 6 over on the whole row. And it is. Oxygen is in family 6. We all right with that? So far, okay? Okay, let's do another one. I don't know, you tell me what you want. Fluorine? Is that what you said? F. Okay, fluorine. Oh man, I almost had it muted the whole time. All right, so we're drawing this sketch real fast, and then I want you to put this in parentheses. I want you to put an N. Over here in parentheses, I want you to put an N. In the D, I want you to put N minus 1 in parentheses. And in F, I want you to put N minus 2. Now, because of the ways that the energies of these D's and F, like their shapes, they're slightly less energies than the full jump, so we write them in between, sort of. There's a whole section, you should read about it if you want the details of why, but we don't have to understand why. we have to understand that when we write the number for a D, we don't write the row number, we write the row number minus 1. And if we were doing F, we would write the row number minus 2. So follow me here. I'm going to do vanadium. So vanadium lives right here. Right there, right? 3 over. Okay, so it's 1s2, 2s2, 2p6, 3s2, 3p6, and then I'm in 4s2, and that takes care of these two, right? But now I go to D, so I subtract 1. It's 3d3. Is that terrible? Oh, it's medium bad, not terrible. Okay, if I was drawing the boxes for this, so after 4s, they put them over here. And we would call these the 3D. And after that, we would have 4p right there. What happened to the what? Why is it sideways? Because it's kind of, it's in between the energy of 4s and 4p. F, we're just going to subtract 2. Okay, tomorrow we're almost done. This is pretty much the last thing. I would read those sections so that you feel better about it. And then tomorrow we'll wrap it up and review, and we'll test on Friday still. Please bring food. A lot of people need you to help them.